Bismillahirrahmanirrahim. Welcome back to my channel. I'm so excited about this video. I just came across this particular topic that deals with signal detection and signal analysis. I mean, this is probably the best topic when it comes to like detecting spectrum monitoring or detecting jammers or detecting transient burst or RF interference, and specifically for satellite communication. The topic is generally known as spectral kurtosis. So basically, what is it that we're trying to do in this flow graph, in this demo, to explain what spectral kurtosis is? So the reason we use this is basically used for like signal analysis and to detect activity in your spectrum that is non-Gaussian activity. So for example, a jammer might have a burst or a signal that is very low, but you won't be able to see it when you do a normal FFT analysis. But spectral kurtosis allows you to see those smaller signal, which isn't present in your frequency band, but you won't be able to see it. So that's the idea behind this. So sometimes the signals are present, but you won't be able to see it. So spectral kurtosis allow us to see those signals. Let's say a signal that has a very smaller strength, which FFT won't be able to do it. Spectral kurtosis allows us to do that. So in this demo, I'm going to show you that, and the idea is quite simple. That we have a source here that is RTL-SDR sourse, and that is going to detect signal that is tuning into different frequency range. So my RTL-SDR dongle that I'm using, it has a range from 50 megahertz all the way up to 945 megahertz. We're going to try to see do a signal kurtosis on FM signals and try to look for something at GSM band as well. So we will be able to see that will I be able to detect any signal, because if a signal has a Gaussian profile as per spectral kurtosis, you won't be able to see anything. You would get a spectral kurtosis to be 0. Anything other than that, you might get some value. Based on that, we're going to do this analysis. RTL-SDR is capturing the signal, is going into a frequency sync, so we can monitor the signal as is, that what type of a signal we're seeing. So we can make a comparison that what will happen if we just do a simple signal analysis using FFT sync, and what happened when we do signal kurtosis. Then this is, excuse me, then the signal is going to an stream to a vector block, then it's going to an FFT block. So right now you're just simply monitoring it, just like in your spectrum analyzer. You have an RTL-SDR source and you have a frequency sync. You're just looking at the signal. Then it's going to a stream to vector block, then it's going to an FFT. Why? Because I have to take FFT signals and then it's going to a block, which is a Python block, which is known as spectral kurtosis. And we're repeating these symbols at interpolation of 100. And then we're looking at it in terms of a GUI, vector GUI sync. Let me explain what's going on. Why do I need an FFT block? So in order for me to do that, there's a paper that gives me the definition of this. So the reason, this is why I need to take that FFT. So this is what is being performed here. If you were to look at my Python block, so this needs to be done. So I'm taking the samples XIM. Endpoint DFT is performed on each of these segments, giving the random variable XIM, where I is going from 1 to M. So this is what's being done. That's why I need a Python block. And inside of this, now if you were to look at this, they're all being summed up. Now if you were to look at this, this is known as fourth power. Fourth power basically generally means that a noise generally has like a fourth momentum. So that's why we're taking it to a fourth power, because that's where the noise is stable when we're performing those kurtosis. And XIM, doing those same samples that we're going to receive from this FFT block, this is being squared. If you were to look at it, so basically we're looking at the fourth power of my samples divided by the power of average power of my average power of those samples. If you remember it from the definition of power definition, power is basically a summation of these absolute value squared of that. So that's why you're getting this squared. So fourth moment, fourth squared divided by the 2, which is basically the power. So in this definition, you're dividing, we're calling this factor a peakedness factor. That's where the peaks are, divided by the power itself. And M is the number of FFT average, number of FFT averages that you're taking. And you're just basically summing them up and these are just the factor that is actually your averaging type of a factor. So basically, fourth peakedness divided by your power. You're taking a division of that because we're summing them up, just like in a power definition. If you recall this from signal and systems, and when you take an average, you will get this K number. Now, these K values are very important. This paper further described that after you perform this operation, this K value, when you get a K, a Gaussian noise will have a K profile of 0. And anything other than that will get a profile, anything other than 0 would tell me that, you know what, this is a different type of a signal. It's not a Gaussian signal. Basically, so you're trying to omit Gaussian signal, a Gaussian profile signal, generally known as noise, and you're trying to detect other signals which are present in your spectrum. A very beautiful idea of spectral kurtosis. Let's look at it and let's look at the demo. So now when you look at this, so this is where these samples are taking place. FFT is going inside, M is 781. Why? Because you're decimating it at the same point. So this is just the decimation factor that is given by sample rate divided by NFFT, which is your sample rate is 3.2 mega samples, and NFFT size is your 4,096 samples, and you're rounding them off to a value. So once you have this, you're just simply now looking at the signal. So I have my RTL SDR dongle plugged in, and I'm going to hit play, and I'm going to look at this. That's the coolest thing that happens. Now, when I look at this, I have my RTL SDR dongle connected. I don't have a version 4. I'm using a 50 power RTL SDR dongle. Let's look at this. So anything like this, I am considering this my signal. So this is the graph. This is the actual spectrum that you're seeing from that RTL SDR dongle that we normally expect to see from a spectrum analyzer. This is that signal. Let me bring this up again. And this part, this right here, this is that signal that you're getting it from that spectral kurtosis box. Now, if you were to look at it, this is the presence of a signal. That's why you're seeing all of this. All right. Even though you're seeing a signal spike right here at this point, but you're not seeing much of a signal here. But let's recognize this here. Just right here, if you were to look at it, you're seeing that that spike. That means that shows the presence of your signal, and this is what's happening. Now, if I were to move on a little bit else, let's say 94. All right. So this is a signal. That's why you're seeing this signal as well. And let's look at some smaller spikes as well. Like, for example, if you were to look at this, this looks like a very small signal. That's why you're seeing a graph that looks something like this, if you guys can see this. And then you can also see this is also a signal. That's why you're seeing this graph. Anything else is considering this as a Gaussian noise floor like this. It depends on your antenna as well, but that's what's going on here. Let's try some other signal. Let's say 100 megahertz, which is also, here we go. So this is that signal, and this is what you're seeing right now. You're also seeing this as a signal. You're seeing this as a signal. Anything other than that is just considering as to be a noise floor. Let's try, let's say 101 megahertz. Here we go, 106, 104 megahertz. So that's what it's detecting. So based on this signal, it's actually telling me, okay, right here, if you were to look at it, it shows that there is no signal, but the spectral kurtosis is showing me that, you know what, at this point, there might be some signal activity. Same here. Now, let me try to move on to, let's say, some 935 megahertz, which is somewhere close to GSM, a downlink, GSM 900. Let's see what's going on here. Here we go. So this looks like, okay, all right. This looks like a signal. So you can see this is a signal. This is also a signal. There's a lot of signals which are there. Even though it looks like a noise floor, but based on spectral kurtosis compared to this, there is a presence of a signal. Let's try something like 942, because my dongle goes up to 942. Right now, it's not showing me anything. I'm going to turn this off, and I'm going to show you in the presence of a jammer. All right, I'm going to turn this off. I'm going to disable this. Now I'm going to use my hackrf. I'm going to enable this, and I'm going to connect my hackrf with an antenna, and then I'm going to show you a signal at 2.4 gigahertz because my dongle doesn't go up to 2.4 gigahertz. Or let's try something like around 1800 megahertz or something like that. So let me try something 875 megahertz. All right, not seeing anything. 825, not seeing anything. Let's try 2.4. All right, this is what it looks like. A signal that is present. I mean, at the Wi-Fi frequency. I need to probably tweak some parameter here. Let me try 2.43. Let me try 2.43. All right, here we go. Now you can see this because generally Wi-Fi signals are so small. Even though my noise floor is saying there's no signal that is present, actual signal, but you can still see that the presence of the signal. So in this way, you can detect signals which are not there in your normal spectral analysis. You don't get to see those signals, but you can see using spectral kurtosis that you will be able to see those signals. Now, let me introduce a jammer here. All right, this is what it looks like. This is what a spectral kurtosis signal looks like. All right, even though you're not seeing on your normal spectrum analyzer, but you are seeing the presence of a signal because you're receiving those signals from your Wi-Fi, but you're not seeing it here on your spectrum analyzer. Now, when I introduce a jammer, all of a sudden you will start seeing what's going on. All right, this is what I wait for it to see your other signal, which is your actually Wi-Fi signal. So that's the idea. This is a very cool device that allows you to actually detect these unexpected signal which you don't get to see on your spectrum. Using spectral kurtosis, you will be able to see those signal that you won't be able to see using a normal spectrum analysis, using normal NFFT, or using a normal what do you call your spectrum analyzer or anything like that. So I hope you find this small video helpful. I hope it will help you. If you have any questions, just leave it in a comment section, and I'll probably put up this flow graph as well on the GitHub repository. And appreciate it. Thanks for watching, and don't forget to like and subscribe to my channel.